Hello, X376 staff members. Today, for my IA application video, I've gathered a couple friends here in the room with me, and I will teach them some computer science. So here it goes. Hello, friends. My name is Mikhail Sashko, and today we'll prove to you that there are some things that computers can't do. I think this is very fascinating because, in my mind at least, it's counterintuitive. I've always felt that if you know everything about some problem, you, given enough smarts, given enough resources, enough time, you're going to be able to write a program or build a computer that can solve that problem. That's just sort of an assumption you pick up, and you have to break that at some point because it's false. And I'll prove to you that it's false in this way. So to prove something so general about every computer, we need to generalize what a computer is, because if we prove something for my laptop, it might not work for your laptop, right? So for the purpose of this proof, a computer is going to be a very simple thing. It's going to be a black box that decides a decision problem. It gives you a yes or no answer to a yes or no question. For example, you could have a computer that decides whether a number is positive. It would take as input a number and say yes if it's positive, and say no if it's not positive. So here I have drawn a computer. I have called this computer M. This is just some arbitrary computer. It can take in anything. Could be a number, could be a string, could be another computer. If we want to judge some properties of a computer, we could have a computer that looks at a computer. And the possible outcomes when you run this computer on some input are the following. There are three possible outcomes. Either X is a solution to the decision problem that M decides. In that case, it's going to say yes. X could be not a solution to this decision problem, in which case it would say no. Or, and this is very important, the third case is if you give it some sort of input, it's entirely possible that it will cause that machine to get stuck in a loop, to go back and forth between states without ever giving you a definite no or yes. In that case, we say that M loops. It loops between some states, never gives you an answer, just keeps on running. You never know what's going to happen to it in the end, right? So here's the problem that cannot be solved by any computer, will never be able to be solved by any computer on this earth, on another earth, in another universe. Nothing can solve this problem that I'm about to describe to you. Suppose you just built a computer that decides something, that takes in a number, for example, and tells you if it's positive. The problem is, I would like to write a computer that takes in this computer and an input to it and tells me whether eventually it's going to say yes or do something else. So here I have a description of this computer. Let's formalize a little bit. This other computer C takes in some computer M and some input to the computer M. And if M says yes, then it also says yes. And if M doesn't say yes, it says no. This might seem like a very simple thing to write. If I just want to know whether this will say yes, why don't I just run M and X and look at what it says? And the reason that doesn't work is this third case, when this machine loops. If you simply try running M and X and from the output figure out whether it's going to say yes or no, and if M ends up looping on that input, then C is also going to end up looping on that input. And we don't want that. If M ends up looping on X, we want it to say no. So that's why we can't do that. That's what makes this a non-trivial problem. That's what makes it interesting. And my claim is that it's impossible to do such a thing. It's impossible to write this computer that'll figure out whether some computer will accept some input or not. So how do we see for ourselves that it is in fact impossible? Well, the way we'll see that is we're going to get a paradox. How will we get a paradox? The way we get a paradox is we define a third computer. We define computer D that does a very simple thing. It takes in one computer only, and then it makes C run M on itself. It makes C ask the question, will M accept itself when you give it itself, or will it do something else? That's what C does. But what D does is it takes that answer that C will give you and it flips it. So if M does accept itself, then C says yes, and D says no. Says no. And if C takes an M and M doesn't accept itself, then C is going to say no, and D is going to flip that answer and it's going to say yes. Pretty simple computer, really only duplicates an input and flips the output of C, but this causes a paradox when you consider what happens when you run D on itself, right? D takes in a computer, it can be any computer, no one's saying it couldn't be itself. So we can run D on itself. And if we do, let's think about what happens. So we give it to here, it passes it on to C with D and D here, and C will tell you whether D accepts itself. So suppose C will tell you that yes, D accepts itself. D takes in itself, solves some decision problem, makes some judgments and says, yes, this is a solution to that problem. So what happens here? If this says yes, D accepts yes, this flips the output and D says no. In other words, if D accepts itself, then D says no. So D doesn't accept itself. And that's a paradox. That's impossible. Those two things contradict each other. They cannot be true at the same time. So let's look at the other way around. Maybe something is going to happen there, right? Who knows? So suppose we give D itself. It's going to pass it on to C, and C is going to run whatever code it has inside of it, and it's going to say no. D isn't a solution to the problem that D solves. D doesn't accept itself. Well, what's going to happen here? If this says no, doesn't accept itself, D flips the input and says yes. In other words, if D doesn't accept itself, when we give it to itself, it's going to end up accepting itself. That's another paradox, just the other way around. So what does it mean? When you get a paradox like this, by making correct logical steps in a certain order, it means that at some point, one of your assumptions or something you took for truth is not truth, it's false. So here, we didn't really assume that many things, we only made logical steps. We only assumed one thing, and that thing we assumed is that this is possible. We assume that it's possible to write a computer that'll tell whether something accepts some input. And we got a paradox, which means our assumption was wrong, and you cannot write such a computer. End of proof. So, any questions about where this works?
No.
Not really? Okay, sure. I hope that's because you understood everything. And
Yeah.
not because you didn't understand anything. Okay, that's fine. Okay, well, I think that wraps it up. Thank you for listening and goodbye.